So we've learned how to count significant figures, and now we're going to use those significant figures to help guide us when we do calculations based on the measurements that we've used. Now, the idea here is that when we do calculations, we can't end up with answers that are more precise than the measurements that they're based on. We made our measurements. We could only make them precise based on the equipment that we used. We can't then, by multiplying and dividing our measurements, make our answers to calculations more exact or more precise than our measurements were to begin with. But at the same time, we don't want to lose track, we don't want to lose any precision if we can help it. So we want to be as precise as possible, but we have to follow a set of rules or guidelines to keep us from going overboard, to keep us from introducing information with calculations that really isn't there based on what we did in the lab. So we're going to find some rules that we have to follow. And again, here's the idea. When you do calculations that are based on measurements, your answer can't be more precise than the least precise measurement that you used in the calculation. So you're limited in your calculations, or the precision of your calculations, by what you did when you made the measurements. All right, so when we calculate, sometimes we're going to add, sometimes we're going to subtract, and when we're doing addition and subtraction, here's a rule we've got to follow. Our answer has to be rounded to the same number of decimal places as the measurement with the smallest number of decimal places. Okay? Let's look at an example. That might make this more clear. So here we have three measurements of length that somebody took. 22.1 centimeters, 14.75 centimeters, 66.001 centimeters. And we want to add all those measurements together. Okay? So when we do add them together, we could get out our calculator, we could do that, and what we would find out is that we would get a number that was 102.851 according to our calculator. And when we add things that have the same unit of measure, that unit of measure is part of the answer. So this is 102.851 centimeters. However, we are limited in the precision of our answer by the least precise of the measurements that we added up. And the least precise measurement is the one that has the fewest number of digits to the right of the decimal point. So this has one digit to the right of the decimal point, in other words, one decimal place. This has two decimal places. This has three decimal places. So our answer, when we add it up, is not 102.851 centimeters. It's this number rounded off so that it has one decimal place. So we want to round off to the tenths place. And to do that, we're going to look at this number right here. We're going to look at this. And we're going to see that this number is 5 or greater. So we're going to round this number 8 up to a 9. So our actual correct answer for this problem is going to be 102.9 centimeters. And that answer has the correct number of significant figures. Here we are right here. We added these three numbers together. Our answer has to have the same number of decimal places as the measurement that had the fewest number of decimal places. Now, if we're going to multiply and divide, as we often are when we do calculations with measurements, we're going to follow a slightly different rule for that. So when we multiply and divide measurements, our answer has to be rounded to the same number of significant figures, not decimal places now. Multiplication and division is different from addition and subtraction. So in this case, our answer has to have the same number of significant figures as the measurement with the smallest number of significant figures. Let's see how that might work. So somebody made two measurements of length, 8.3 meters and 2.22 meters. We're going to multiply those two things together. When we're multiplying, we're going to multiply the units. Meters times meters is meters squared. And we're also going to multiply the numbers. Now, let me make the screen a little smaller here so we can get out our calculator. And let's multiply 8.3 times 2.22. And when we do that, our calculator says that the answer is 18.426 meters. Let's write that down. I'm going to write it down below here. 18.426 meters. Actually, meters squared it is. Meters times meters is meters squared. All right, now, this answer, 462, this answer has many more significant figures than the measurements that we started out with. And we cannot end up with a more precise answer than we started out with when we did our original measurements. So we look at our original measurements, we find that this one has 2 significant figures and this one has 3 significant figures. And when we multiply them together, we're going to end up, we can only end up with an answer that has 2 and no more than 2 significant figures. So we need to round this number off so that it has 2 significant figures. We're going to round off to the ones place. So we're going to look at this number, this 4, it's 4 or less, so we're not going to change the 1, so we're not going to change the 8, that is. So the correct answer to this problem is 18 meters squared, in spite of what our calculator says. Our calculator can do the multiplication, it doesn't know about significant figures. All right, how about another example? And to get to that other example, we'll go this way. What if, here's our answer, what if we want to figure out the density of something by taking its mass and dividing it by its volume. So we've got this object. We measured the mass as 22.04 grams. We measured the volume as 18.0 milliliters. We're going to divide mass by volume. First we divide the units. We get grams over milliliters. The units are part of the calculation. And now we have to divide 21.04 by 18. Let's see how that comes out here. 21.04 divided by 18. Whoops, I did that wrong. Let's go back again. 21.04 divided by 18. 18.0 equals 1.1. And then a whole bunch of 6s until finally the calculator runs out of room to write 6s and it rounds it off. Okay? So you might think that the answer to this problem was 1.1666, the 6 continuing forever. But that would be incorrect because we cannot write down an unlimited number of 6s in this measurement, in this calculation, because our measurements were limited by the equipment that we had. So in this measurement of volume, we had 3 significant figures. In this measurement of mass, we had 4 significant figures. Our answer should have the same number of significant figures as the measurement with the smallest number. So our measurement, our answer, our calculation, is going to have 3 significant figures. So we're going to round this off, this answer off to this number. We're going to do that by looking at this number here. And we find that this is 5 or greater, so we're going to round the 6 up to a 7. And the correct answer to this problem is 1.17 grams per milliliter. That is an answer that has 3 significant figures. Let's see how we did. Oops. There we go. 1.17 grams per milliliter, not this number that our calculator gave us. Right? All right, now we have a way to get the correct precision when we do calculations with measurements, and that is by using the number of significant figures in the measurement. So every time we do a calculation based on a measurement, those significant figures are going to guide us to how to correctly write the answer. So there's a look at using calculations. Here's a summary of our rules for addition and subtraction and multiplication and division, and we can now calculate using significant figures.